Hey everyone, let's review the EpiChem FRQ, the first question. The first question asks to complete the electronic configuration for manganese. To solve this question, we need to go back and review our periodic table, okay, which I have it here. So for manganese, as we can see, this is our manganese, right? So based on the periodic table, we can see what we have. 1s2, right? 2s2, 2p6, 3s2, 3p6, 4s2, and then this one is 3d1, 2, 3, 4, 5, 3d5. So the answer is gonna be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. Okay. Now, the second question asks, when manganese forms cation, the electrons are lost from which subshell first? So, when look at this, you will think that it will go from the 3D, but no, because 3D is not the valence shells. The valence shell is actually 4s. See, it's bigger in the principal quantum number. So this is the valence electrons in the 4s. So it's gonna be taken out from the 4s first. Okay. The next question, student perform experiment to produce a manganese salt of unknown composition, MnxCIy. Determine its empirical formula. The student placed manganese in a beaker containing hydrochloric acid, blah, blah, blah. And this is the given chemical equation. Okay, now let's just write the chemical equation, the given chemical equation here. So we can just have a look at it. So we have X Mn solid plus Y HCl aqueous MnxCIy plus Y over 2 H2S. Okay, now the student heats the result mixture until manganese chloride remain in the beaker, until only manganese chloride remain in the beaker. And these are the data. Okay, so here we see that the mass of empty beaker is this much, right? And when we add the manganese, it becomes this. And once the manganese is all reacted and leaving us with the manganese chloride, this was the mass. So the question asks, calculate the mass of chlorine in the manganese chloride. Okay, so first we just need to find the mass of manganese. So which is gonna be what? The mass of manganese and beaker, which is this one, minusing that one. So we have 61.262 gram minus 60.169 gram. And we're gonna get, sorry, we're gonna get 1.093 gram. Okay, now we want to find the mass of manganese chloride. So this is also the same. We take this value and we minus with the empty beaker. So we have 62.673 gram minus 60.169 gram. And this is going to give us 2.504 gram. Okay, so look at this. So we have manganese chloride, this much, and we have manganese, this much, right? So with the law of mass preservation, we can know that the mass of chlorine is just going to be of what? The mass of the manganese chloride minus the mass of manganese. So it's going to be 2.504 gram minus 1.093 gram. And that's going to give us 1.411 gram. Okay. So now we want to find the number of mole of chlorine, right? Number of mole of chlorine. So number of mole, right, is equals to what? Moles, if you know, moles equals to given gram over molar mass. Or you can use the dimensional analysis way to find the answer. But yeah, it's just the same thing. So we take the 1.411 gram divided by the molar mass, which happens to be, let's check it out, for chlorine, it's 35.45. So 35.45 gram per mole. And we're gonna get 0.03980, but because we want to be exact with the sig fig, it's gonna be 4 sig fig. So it's just gonna give one more zero there. Okay, there we have mole of chlorine. So now we have our mole of chlorine. Now the question says, okay, let's say a student determines that the mole of manganese is this much, and they want us to find the empirical formula if that was the mole of manganese. So if you know that we can find the empirical formula based on the mass of the moles, so let's just do with the what? So once we have the moles of manganese, which is to be 0.0199 mole. And we also have, or else we can just make a table, sorry. We can just make a table. So this is for manganese, this is moles, and this is for chlorine. And chlorine, we just found out that it's supposed to be 0.03980 mole. And now the way we can find the empirical formula is to divide with the lowest mole. So 0.0199, 0.0199. So this is going to give us 1, while this is going to give us 2. So the empirical formula is going to be MnCl2. Okay. Now, student repeat the experiment using the same amount of manganese and HCl. And notice that some of the MnCIy sputtered out of the beaker as it heads to dryness. Write the number of moles of Cl. Will the number of moles of Cl calculated in this trial be greater than, less than, or equals to the number of the one that's calculated in part C? And we need to justify our answer. So basically what they say is that the amount here is going to be lesser than the amount given here, right, in the second experiment. So when this amount is lesser, what's going to happen is that the gram of Cl is also going to be less. And when the gram is going to be less, the number of mole of Cl is definitely going to be less. Yeah, so that answer the question that the number of Cl is actually going to be less if we couldn't preserve all the manganese chloride. Okay, so what we're going to write here is the numbers of mole of Cl will be lesser than the calculated than the one calculated in part C, because we found out the mass of Cl, sorry, by subtracting the amount of manganese chloride by subtracting the amount of manganese from manganese chloride, and if the amount of manganese chloride is less, that's gonna result in lesser amount of chlorine, therefore lesser mole of chlorine. Okay, now now coming to this question. Now coming to this question, based on the half reaction given in the table, write the balanced net ionic equation for the reaction. Okay, so this is the keyword here. That has the greatest thermodynamic favorability. Okay, now when is it that reaction is most thermodynamic favorable? It is when the delta G is the most negative. Okay, so if it's the most negative, right? And how do we relate delta G with the E naught? So we relate it by NF E naught, negative NF E naught. So if we have a higher value of E naught, that's gonna make what? That's gonna make the delta G become more negative and therefore more favorable. So we need to figure out in such a way that we have the highest E naught reaction. Okay, so E naught reaction, and if you know that E naught reaction is going to be E cathode minus E anode. So E cathode, so which one's going to be our E cathode? E cathode is going to be the one that has highest E naught. So in this one, we have, this is the highest E naught. So that's going to be our E cathode. So which is going to be 0.15 minus, and our E anode is either these two, either this one or this one. But if we want to have the highest E naught reaction, we need to choose the one that's the lowest, right? So that means this one. So we're gonna minus 1.28, and this is gonna give us 1.43 volt. Okay, this is volt, this is volt. Okay. Now, let's go to the next question. Oh, sorry, this is supposed to be the answer to this one. Okay. Okay, now we know that this is going to be our E, and this is going to be our cathode, and this is going to be our anode. So what we know that cathode is where it's going to reduce, and anode is where it's going to oxidize. So if it's going to oxidize, that means it's going to release electron, not taking an electron. See here, it's taking an electron. It's supposed to release electron. So to release the electrons, this reaction needs to flip. So that means it's going to be zinc plus 2 OH AQ becoming zinc oxide plus H2O liquid plus 2 E0, 2 electron. And the other one, this one is just going to stay as it is, which means H2O liquid plus 2E electron becoming Mn2O3 solid plus 2 hydroxide aqueous. Now, we are just going to add up these two reactions. And from here, we can see, we can just start canceling whatever that is the same. So that's going to cancel. Electrons going to cancel. And hydroxide is also going to cancel. So in our net ionic equation, we're just going to get plus 2 MnO2 becoming zinc oxide plus Mn2O3 solid. Okay. Now calculate the value of delta G in kilojoule per mole reaction. So we know that delta G is negative NFE naught. And this is what? Minus, okay, what is our N? N is the number of electrons being transferred. So here, if you can see, on these two reactions here, we have 2 electrons is actually being transferred. You do not add this 2 becoming 4, okay? It's just 2. It's just from this reaction, it's transferred to this reaction. That's it. So just 2 electrons being transferred. So we take 2 minus the Faraday's number, which is 90, it's here somewhere, 96,485. Okay, 96,485 coulombs per mole. So we have 96,485 coulombs per mole. And our E0 that we already calculated is this one, 1.43 volt. So one thing that you need to know is that the volt here, okay, the volt here is actually your joules per coulomb. Okay, the joules per coulomb. So now we can calculate, we can calculate this and get our answer as negative 276,000 joules per mole. And but the question 1 in kilojoule per mole, so we just need to convert the joules into kilojoules, and it's going to become 276 negative 2 kilojoule per mole. Okay. And coming to the last question here, I guess. Yep. So in chemical, so in redox we have what? 1 anode and 1 cathode, right? So let's see. In this example, we have anode as our zinc and our cathode manganese, right? So anode is our zinc and cathode is our manganese. So that means manganese is the one that get reduced. That means what? You have the manganese from the solution becoming manganese solid, right? This manganese that was in the solution, it is what? It is in solution, but then it deposits and become mass, right? And the zinc, which is our anode, it get oxidized. That means, let's say this is just zinc solid, and it get oxidized to become zinc 2 plus aqueous plus electrons, 2 electrons. So in this case, you can see that zinc solid, which is mass, converted into aqueous, which means it's just in the solution. That means in the anode, we are losing mass. But in the cathode here, we are actually gaining mass. So overall, the total mass of the battery is just gonna stay the same. Okay, so this is the law of our conservation of mass. Okay, based on law of, so you can write based on the law of conservation mass that the cathode's gonna the cathode's gonna reduce, and that means it's gonna gain mass, while the anode's gonna oxidize and it's gonna lose the mass, but overall it's just gonna stay the same. There is no losing of mass in the whole when we take account the whole battery. I hope this is helpful for you. Thank you for watching.